Hello everyone. Please do not forget to put plus on the YouTube commentaries. Okay, so let's start. So last time we finished with just let me check. So we had exercise 5. So we made the 5A, right? So let's proceed with 5B, right? So in this case, we have to give an examples of sets A and B such that A is not an element of B and A is a subset of B. So what can you tell me about this one? What example can we have here? So we need two subsets such that they don't, so that A doesn't belong to B. So A is not an element of B, but A is a subset of B. So in this case, for example, we can have, I don't know, if A is 1 and 2, right? Then B can be 1 and 2 and 3, for example, right? So A doesn't belong to B. We can see that because this is an element. I mean, the element A, the set A, is not here. We have 1 and 2, right? But we don't have the set 1 and 2. So this holds. And what about this one? So the definition for this one is that A is a subset of B if all the elements of A are elements of B. Okay, so all the elements of A, we have 1 and 2, are elements of B, 1 and 2 as well. Yeah, this is true. So for this one holds. Okay, but this is just one of many infinite examples that we can give. But I want you to get the general idea here. So I want you to give me the general example here. So what if, for example, B in this case, so B prime, let's call it, is equal to 1 and 2, right? A is the empty set, is correct. Well, it can be the empty set, sure. But okay, what if we have this A and this B prime here? This does this hold? What do you think? Tell me yes or no. So we have that A is the set with elements 1 and 2, and that B is the set with elements 1 and 2 as well. So A is equal to B prime, right? So in this case, this holds, yes, right? Why? Because by definition, we say that for any sets, if A is not an element of itself, right? By definition, by the axiom of foundation, this is true, right? So if we have that A is equal to B prime, then A doesn't belong to B prime. This holds. That's good. What about this one? Is this true for all A? All these sets are subsets of itself? Yes, right? Because all the elements in A are elements of A, right? So it means that for B prime, for A equal B prime, so for this A and this B prime, this holds as well. So the general case the general example, I would like to call it that way, general example is any A equal B. Now any A and B such that A is equals B. Okay? So if we have A equals B, then this holds in the general case, right? Not the only one, not the only one, because we have here that A is not equal to B, right? But this holds. So, but in any case, if we have any A and B and they are equal, then this holds. Okay? I hope this is clear. So we can move forward with 5C. And in 5C, we have to give an example of A that belongs to B, and A is not a subset of B, right? A belongs to B, but A is not a subset of B. Of course, here we can create some example, right? I don't know, like for example, take A 1 and 2. No, just A take 1, and take B. No, take, not a subset. Wait. If A is 1, then we can take B as an element, and B is not a subset, I don't know, and 2, this one for example. So we can see here that for A and B this holds, right? We have that A is the singleton or singleton of 1, right? And B is the singleton of 1 and 2. Now this A belongs to B. Yes, we can see that. But what about this one? Is A a subset of B? No, it's not, right? It's not, because here A is an element but not a subset. Okay? Why? Because what are the elements of A? Just 1. All the elements here are just 1. And the elements here are the singleton of 1 and 2. And 1 is not equal to the singleton of 1. We will see that later. And 1 is not equal to 2. So for this A and B, this holds, right? But anyway, still I would like to give you a more general case. And what if we take, for example, A equal some subset, some set A. What B can I write such that this holds? Who can tell me? So I want this to be true, and I know that A equals A. What B should I take here? So I want A, little a, to be an element of B, but I don't want it to be a subset. Can anybody tell me? What about, look at this A here. What are the elements of the A here? Well, yes, Mustafa, but without, just A, the singleton of A. Yes, right? So A is an element of B, yes, because A is the only element of the singleton of A, but A is not a subset of the singleton of A. And you prove that in your lecture, right? You prove that in the lecture, so I'm not going to prove it right now, but you prove this in your lecture. So A is not, so A is an element of the singleton of A, yes, but A is not a subset of the singleton of A. You should have proved this on your lecture, okay? So this is a general example that works for us here. And yeah, and this one is enough. So look, again, we have that in this case, in 5b, all we need is AB to be equal, for example. For A, B equal, this holds. And then 5c, for A, any set, and B, the singleton of A, this works as well, okay? So A is not an element or something, A is a set. For example, A can be, I don't know, the set of all the natural numbers, right? So the set of all the natural numbers can be A, and B can be the singleton of the set of the natural numbers. And we have this here, okay? Good, so that's for 5C, and we still have 5D. So I will write it here. By the way, so tomorrow is the deadline for homework 1. I will check these solutions that you sent me till today, right? Till now. And I know that in our Excel file, we didn't have, I think that I was hoping to see 14 of you to subscribe in our Excel file, but I only saw 11 or 10 or something. So what about the others? So look, we are going to do the following. If you have your solution, but there wasn't any free space on the Excel file, please write your name at the end of the file, at the end, so you can just add your name right now. I'm going to look at this list after the seminar. I will look at the names here. I will look your solutions on your Google folders, and I will discuss that solutions with you tomorrow, okay? So if there are not free spaces in this file, just add your name at the end of the list. I will listen to everyone, okay? 20 minutes is going to be enough, do not worry. The only difference is that this time, if you have something wrong, well, it will be wrong, and that's it, right? But if you presented the solutions last week, so you had an extra week to correct them, and just present it again, right? But this time, if it's wrong, so it's wrong, and that's it, right? So do not forget about that. So I'm ready to listen to everyone, okay? Okay, and tomorrow we will discuss only homework 1, right? Next week we start with homework 2. Homework 2 is not easy, so please pay attention to that. So 5D. By the way, this semester you get a grade from 1 to 10, okay? From 1 to 10. So that will be depend on your grades of your homeworks. Don't forget it. 5D. Where is 5D? Yes. So we need to give an example of A and B such that A belongs to B, and A is a subset of B. So we already have the 4 cases. Yes, and the last one was this, that they both belong to each other. So A belongs to B and A is a subset of B. So who can tell me what ideas do you have here? What example? So of course we can think about something trivial, like I don't know, if A is just 1 and B, for example, this thing, this. So it works, right, for this case. So A is an element of B, and A is a subset of B as well, right? Because the singleton of 1 is going to be a subset of B, right? And the singleton of 1 is as well an element of B. So we can think about something like that, of course. So we have A and yes, good. Yeah, and then we have to think about this one in the following way. So let's take, for example, A equals the singleton of the empty space, right? Then B is going to be what? It's going to be the empty space and the singleton of the empty space, right? Now, who can tell me what is this? What is this set? How can I get this set from A? What is the relation that I have between this set A and this set B? Who can tell me? So let me remind you, what is the name of this? The power set, right? The power set of X. And the power set of a set, what is the power set of a set? It's the set of all the subsets, right? So this is the set of all the subsets of X, right? Now, what is the power set of the empty space? Of the empty set, sorry. What is the power set of the empty set? Is the empty set. You proved that on your lecture, I think. Now, what about the power set of the singleton of the empty set? So first of all, every time we look at the power set, the first element we have to write is the empty set, because the empty set is a subset of any set. So the empty set, right? Now what else? We know that we know this. Any element, any set is a subset of itself, right? So we have to write the element itself, so the singleton of the empty set. So we obtain that this is equal to the power set of the singleton of the empty set, right? So in the general case, all we have to do is to put A equal to the singleton of the empty space, for example, and B is going to be the power set of A. Okay, I hope this is clear. Yeah, that's it. Good, so we already review all the 4 possible cases, and this is going to be really useful for you. You will see it. Now we can proceed with exercise 4, because we didn't resolve 4 the last time, so let's resolve 4, number 4. 1 second. So exercise number 4. Prove that these sets A and B, B and C is not equal to the set A, B, and C. So we have to prove this, that they are not equal. This is, I mean, we can see it. If we look at this, we can see it, that we can see that they're not equal, of course, but still we have to prove. So what? The power set of, no, the power set of the empty set. So this is a question from YouTube. The power set of the empty set is just the empty set. Okay? The power set of the empty set is the empty set. Now the power set of the singleton of the empty set is the empty set, so has 2 elements, the empty set and the singleton of the empty set. Okay? Okay, so we have to prove this, that these 2 sets are not equal. What do we need to do if we want to prove that 2 sets are equal? So we have 2 options. We can do it by definition, and the definition is that, 2 sets are equal by definition if X belongs to A, if and only if X belongs to B. In that case, A and B are equal, right? So this by definition. We are not going to do that here. The other way is that we know that A is equal to B if and only if A is a subset of B and B is a subset of A. Okay? So 2 sets are equal if and only if this holds. And all these results you obtain it on your lecture. I think you should have obtained it. Okay, so we're going to use this, right? So every time we need to prove that 2 sets are equal, we need to prove this. We need to prove that A is a subset of B and B is a subset of A, right? And now we want to prove that they are not equal. Of course, we need to assume that they are equal, and then we will get some contradiction or something. So assume that these sets are equal. So A, B, and B and C is equal to the set A, B, and C. Right. So it means that we have to prove this for 2 cases. We have to prove this on this direction. So we have to prove that this set here is a subset of this one. So let's show that this is a subset of this one. So let me write this again, just to be clear. So we have to prove that A, B, and B, C is a subset of A, B, and C. Okay. So this is true. If this is true, it means that all the elements here have to be here, right? So let's take this element. So A and B. So A and B. Let's take this element, and this element has to be, so element is equal to A, or this set here is equal to B, or this set here is equal to C, by definition, right? Because all the elements from here should be here as well. So it means that this element should be equal to this, or this, or this one. So we have three options here: case 1, case 2, and case 3. What if this is true? So, case 1, case 2, and case 3. So what if this is true? So we know that A, then, if this is true, then A, we know that A is an element of A and B, right? A is an element of A and B, and this is equal to A. Then A is an element of A. This is not possible, so we got a contradiction here, right? This is not possible. Now, case 2. We know, so if this is true, then we know that B is an element of A and B, AB, and this is equal to B, then B is an element of B as well. So of course we got a contradiction here again. And for case 3, it's okay. We don't get any contradiction. So let's assume, so well, this is the only possible option left. So we're going to take that this is true. So C is equal to the set AB. Okay, good. Now what about this set here, BC? So in the same way, similarly, this has to be equal either to A, B, or C. And if we do this, as we did here, we will obtain that this, that if this is equal to this, then we get a contradiction. And if this is equal to this, then we get a contradiction as well. So because it's going to be that C is an element of C, right? So the unique option we have here, the only option we have, is that BC is equal to A. Then BC, the element BC is equal to A. For this one, we don't have any contradiction yet. So we have that AB is equal to C and BC is equal to A. Okay? But we can see that A is an element of this, right? So from here and from here, we have that A is an element of this set. And A is an element of this set. And wait. So A is an element of C. And this is equal to C, right? and C is an element of BC, so of A. So of BC, since an element of BC, that is equal to A. So we obtain that A is an element of A. Contradiction, this is not possible. Okay. So we already look at all the possible cases, and in each of them we obtain a contradiction. Good. So what does this mean? So it means that we assume something that is not true, right? So thus this set AB BC is not a subset of A, B, and C. Good. Actually, this is enough. If we want to prove that they are not equal, so they asked to prove this. We had to prove that this set is not equal to this, right? And we already showed this, that A doesn't belong to, that A is not a subset of B. This is enough. So we're finished proving that they are not equal. Okay, this is enough. But still they asked, can either inclusion hold? So they want us to prove that, what about this one? Is this true or not, right? So do not forget, this is enough, what we proved before, this is enough for telling that this is not equal, right? But we still have a question here, can either inclusion hold? So what about this inclusion? Maybe this inclusion holds. So let's prove that this inclusion actually doesn't hold as well, okay? So suppose that it holds, so that A, B, C is a subset of A and B and BC, right? And we have to do this, everything we did here, we have to just repeat all this. But in this case, we will have what? So we will obtain, I'm not going to do it because we don't have much time, but it's exactly the same. So we'll obtain that A can be BC, for example. So for A equals BC, we don't have a contradiction, of course. Now, what about C? If C is equal to AB, we don't get any contradiction. So that actually works. But what about B, right? So B, so let's look at B. So B has to be equal either to AB, or B has to be equal to BC, right? And what if this is true? the same. So we know that B is an element of AB, and AB is equal to B. So we obtain that B is an element of B. So a contradiction here, right? And in this case, it's exactly the same. So B is an element of BC, and BC is equal to B. So we obtain that B is an element of B, and this is a contradiction here. What does it mean? It means that, let me write that here, it means that this set is not a subset of this other set, AB and BC. So the answer to this question, can either inclusion hold? No. We proved that it doesn't hold in this way, and it doesn't hold in this way as well, right? So that's it. Number 4 is finished. Good. Now we can continue with number 6. Okay, let me. We have time. That's good. Today, I think we are going to start with exercises number 4. So these are exercises on sets, on set theory. And we are going to start today also with exercises on the binary relations. Okay. Well, I think we're going to start. Yes. We have number 6 and number 7 and 8, right? And that's it. Yeah, sure. So number 6. We have to prove that the set 1, so this with elements 1, with this element x belongs to the natural numbers such that 2x is odd and 1 is equal to the set y integer number such that y is less than y and 1. So we have to prove that this element, so you can call this element A, this the set A, and this is going to be the set B. We have to prove that they are equal. What does it mean that they're equal? That they have exactly the same elements, right? So let's start with this weird thing here, and this one also. So let me write that here. X natural such that 2x is odd. Who can tell me what is the set equal to? This set here. What is this set equal to? So it's the set of all the natural numbers such that if you multiply this number, you obtain by 2, you obtain an odd number. Yes. Empty set. We don't have such natural numbers. What about the second one? What about y? That is an integer such that y is less than y. What is this equal to? So you have a question, why do we write AB equals B and also BC, AB equals B, BC. Look at this Masud, right? Or this is true or this is true. About your question. So what is this equal to? Empty set as well, right? We don't have such integers that this number is less than itself, right? So then we obtain the following sets. So we have the set 1, empty set, and 1, and the empty set and 1. Now tell me, are they equal or not? Are these sets equal or not? So what's the difference between these sets? That we have here the empty set and 1, and we have here the empty set and 1, and 1 once more, right? So we have our repeated element here. So what does it mean? Are they equal? Yes, they are equal. Because we don't care about the number of elements that we have here. I mean, 1 and 1 is the same element, so we only are going to say that, so this is equal to this. When we talk about sets, we don't care about the order. First of all, we don't care about the order, and we don't care about the number of elements repeated. Okay? Don't forget this. We don't care about the order, so the element, the set AB is equal to the set BA. Right? And the set AA is equal to the set A. Okay? Good. Now, we need to prove that they're equal. Yes, so yes, they are equal. How are we going to prove that? So, for all x belongs to this set 1, empty, and 1. If and only if x is equal to 1 or x is equal to the empty set or x is equal to 1. Yes? By definition. So for any x in this set, we have that this is true if and only if x is equal to some of the elements here. But this is equivalent to say x equals 1 or x equals the empty set. So these things, this predicate here and this one are equivalent. So if we obtain here true, this is going to be true. If we obtain here false, this is going to be false, right? So if and only if this, if and only if this one. And this, if and only if x belongs to 1 and the empty set. So we obtain that x belongs to this set if and only if X belongs to this set. By definition, this set is equal to this set because of this, right? So the definition of when we say that two sets are equal, it means that if X belongs, so that X belongs to A if and only if X belongs to B. So X belongs to A, let's call this A, if and only if, right, X belongs to B. So this B and this A, let's call it that way, A and B are equal. So this set is equal to this set. We'll finish the proof. Okay. I hope everything is clear here. Yeah. That's it for number 6. Now we can proceed with number 7. Let's do it over here. So number 7. Prove that the following sets are not equal. So let's prove that the set A with elements AB is not equal to the empty set. Of course, this is quite obvious. I mean, this set has 2 elements, and the empty set doesn't have any element, and we know that the empty set is unique, right? So of course this is not true, but let's prove it. By definition, we have to prove it. You already proved that. So what's the empty set? By the way, what's the definition of the empty set? So the empty set, so let me write here, the definition of the empty set, right, is we said that the empty set is all the natural numbers such that X is not equal to X, right? So no elements are here. This is called the empty set, and we know that the empty set is unique. So if we have the 2 sets are empty, they are exactly the same. We don't have 2 empty sets, different empty sets. Good. So let's prove this. So of course, assume that they're equal. Again, what do we need to do if they are equal? If we want to prove that they are equal, we have to look at all the elements here, and they has to be elements from here as well. Then it means that A and B is a subset of the empty set, and A and B, and the empty set, let me write that, is a subset of A and B. So we have to prove that this is true and that this is true, right? Which one is true already? From the left or the one from the right? The one from the right. Yes. So this is true. Why? Because the empty set is a subset of any set. So we don't care what we have here. Maybe A and B is actually the empty set. Maybe not. It doesn't matter here because the empty set is a subset of any set, including the empty set as well. Okay? So this is true. Now we have to look at this. Is this true or not? So this is true. If this is true, it means that the elements from here has to be elements from here as well, right? So A and B, the set of A and B is a subset of the empty set if and only if, this is by definition, my definition, for all x such that x belongs to A and B, right? So all the elements in A and B, then x belongs to the empty set. Yes, by definition. So this is true if and only if this is true. But this is not true. This is false. We know that, right? This is false. And since we are assuming that this is true, then this is false. Right? And it means that this is false. Because if and only if. So this to be true, if this is false, then this is false and this is true. So it means, so thus, therefore, A, B is not a subset of the empty set. And that's it, we prove it. So the set AB is not equal to the empty set. Yeah. That's it for the first one. So this is 7A. Right? What about 7B? So let's do it here. Seven B is which one? Is that we have to prove that A, the singleton of A, is not equal to A for any A. Right? I think you proved this one on your lecture, but I'm not sure, so I'm going to prove it anyway. Okay. So the singleton of A is not equal to A. So yes, all we have to do here is, so let me remind you the definition of a singleton, and it's still so a singleton. Then we say that for all A, there exists a singleton of this set such that for all X, X belongs to this singleton if and only if X is equal to A. So the singleton of a set is a set that contains itself, only itself, right? So any element of this set is just A. So this is the only element from this set, right? So only A is an element from A. Okay. Yes. So using this definition, so this is true. So let's assume that the singleton of A is equal to A. Then by definition, for all x belongs to the singleton of A if and only if x belongs to A. So this is by definition. So we say that two sets are equal if and only if any element here is in here. Good. Now, let's look at this equation here. Well, not this equation, this statement here. And take x equals A. Right? Well, we can take it for all x. X can be anything. So if we take A here, then we obtain what? A is an element of the singleton of A if and only if A is equal to A. Right? And this is true. A is equal to A. This is true. It means that this is true. So this is true. This is true. This one. So A is an element of its singleton. This is true. And now, what if we take the same here? We have for all x. So take x equals A. What do we obtain here? We obtain that A belongs to A if and only if A to the singleton of A if and only if A belongs to A. And we know that this is true from here. From here, we know that this is true. And we want this to be true. It means that this should be true. So we got a contradiction. Right? Because we need this to be true. It means we assume that this is true, and we get a contradiction because this is not true. And that's it. Then we got, let me write that, we got a contradiction. With the axiom of foundation. So the singleton of A is not equal to A. And the proof is finished. Good. Now we can continue with C. Okay. So don't forget, if you have any questions, you can write on YouTube, and I will try to answer. So we proceed with C. And for C we have to prove that these two sets, a empty set and the singleton of A and the singleton of B, we have to prove that they are not equal. Okay. So again, we have to prove. So we assume that this is true, that they are equal, and then if they are equal, then this is a subset of this, and this is a subset of this. So let's assume that this is a subset of this. I will just write that in this direction, right? So this is a subset of this. Then it means that the empty set has to be equal to A, or the empty set has to be equal to B, to the singleton of B. Right? So if this is a subset of this, then this element should be here. And here we have just two elements. So this element should be equal to this or to this. Good. And so what if, so this is going to be the first case, and it's going to be the second case here. So for the first case, we have that the empty set is equal to the singleton of A, if and only if. Now we have to use the definition of the equality of two sets, and that's that for all x such that x is an element of the empty set, if and only if x is an element of the singleton of A, right? But this is false. And we want this to be true. Well, this is false, and no, sorry. Yeah. So this is false, and since we want, wait. So this is false, and this is going to be so, and this is true. No, wait. So if we want this to be true, so this is false. If we want this to be true, then this should be false as well. Yes, so this is false, and if we want this to be true, then this should be false as well, but this is not false, because there exists an element that belongs to A. That's A, right? So this is true, and it means that all this is false, and then this is false. Okay. So again, this is false, and we want this to be true. But if we say that this is false, we got a contradiction, because there is some x such that it's an element of A. So this should be true, and then all this is false. It means that this is false. So the empty set is not equal to the singleton of A. Yes. And the same for empty set equals B. So we obtain that the empty set is not equal B, the singleton of B. And then we have proved that this doesn't hold. So this set A, the empty set, is not a subset of the singletons of A and B. And then this set is not equal to this set of the singletons of A and B. And the proof is finished. Yeah. So this is enough. So if we want to prove that they are not equal, then we have to prove that it holds for this and for this. But since it doesn't hold for this, so it means that they are not equal. That's it. That's enough. Now, number 8. Is the last one? Yeah, it's the last one. Good, good. So let me write that here. So this is number 8. Translate the following set specification. So the set of all integer numbers less or equal than some root of the polynomial, this polynomial 3x squared, no, 3x to the 5th power plus 14x cubed plus, well, minus actually, minus x squared plus x minus 6 into the form, so into the form that x belongs to A such that some phi of x, right? So we have to translate, yeah, where this reads set x satisfies the property phi. So again, translate the following set specification. The set of all the integer numbers less or equal than some root of the polynomial, this polynomial here, into this form. Okay, so the set of all the integer numbers. So the solution is the following. X is from the set of all the integer numbers, right? So x, so the set of all the integers x such that some property is satisfied here. Which one? That they are less or equal than some root of the polynomial such that x is less or equal than y, and right, where y is the solution of this polynomial 3y 5 plus 14y cube minus y square plus y minus 6 equals 0. Right? So all the integers such that they are less than all the solutions of this polynomial, less or equal than all the solutions of this polynomial. And that's it. Thus, we finish with work number 3. And now we can start with work number 4. We still have 5 minutes. Right. So binary relations. So I have to remember here some definitions. And so I will prepare today, in these 5 minutes, I will prepare all the theory that I will need next seminar, okay? So let me remind you, the first definition is that, so this is definition here, that for all A and for all B, this thing here, AB, is by definition the set of the singleton of A and the set AB. And this is called an ordered pair. Okay, so here we care about the order of the elements. Okay, so look, this is not, I mean, yes, this is a set, but this is not a set of A and B. This is a set of the singleton of A and the set of AB. Okay, so if I ask you, for example, in the exam or something, or in the discussion of your homework, that what is this, and you tell me this is a set of the elements AB, this is not true. Okay, not a set of elements AB. It's an ordered pair that we define like this. Okay, so we have definition of an ordered pair. Now we can define what this is. A, B, A cross B, right? I forgot how to say this in English. Okay, so this is going to be Z that belongs to the power set of the union of A and B, right? Such that there exists some A and there exists some B, that A belongs to capital A and B belongs to capital B, and Z is equal to A and B, to the ordered pair A and B. Okay. Now what about, but we are going to write the following. So this is the formal definition, okay, but we are not going to write this all the time. So this is going to be equal just to all the ordered pairs A and B, such that A belongs to capital A and B belongs to capital B. So all the time we are going to write this, but this is not the definition, okay? The definition is this one. This is just something that is comfortable for us to write, because, well, we don't want to write this all the time. And what else do we need? Okay, yes, of course we have to write what a binary. We don't have time actually. Yeah, I think that's it for today. So next time we start with homework, well, not homework, but coursework 4. And please review your lecture, yesterday lecture. I think that you look at all this. Okay. I wait for you tomorrow, and thank you very much.